These are two other kinds of questions that are somewhat related to the heating curve, and I'm just showing a different way of solving them. So one more note about the heating curve is that these equations, if you remember, this is what Q equals, which is what the heat equals. This is what Q equals. This is what Q equals. This is what Q equals. And this is what Q equals. And you just add up all the Q's. It's additive. So you can also just be working in this, a certain section of this curve, and you can kind of match up what equation you need. Okay, so we've got two problems. One is, what is the mass at 0 that can be frozen? And then one is the enthalpy change? So let's read really carefully. We have liquid water at 0 Celsius, and we want to know how much can be frozen. So we're already at the right temperature. We just need to have it freeze. So we're going to remove some heat. So where we are on this curve is right here. And yes, you could throw it in that equation and you'd be good to go. However, there's a faster way of doing it, I think at least. Remember that delta H of fusion, the value for it is 6.02 kilojoules per mole. That's the value for it. And then we have a kilojoules right here. So you can also do this problem like a factor label. Let's take 5 kilojoules, and then we can say that there are 6.02 kilojoules in 1 mole. And then we can say this is water, so in 1 mole of water, it's 18.02 grams. That's from the periodic chart, just adding it up. We cancel those terms out, and we're going to be left with grams, which is what they're asking for, is the mass of water. So instead of plugging into this equation and then taking your moles, solving for moles and turning it into grams, you might find it easier to work that problem like a factor label problem. That'll work anytime that you're within that, you just want to find out information about the transition. Now over here, what is the enthalpy change if water is heating? So now we're in a different place on the chart. So we've got something that's in this range right here. I'm going to make this like a gray color. It's going to be starting here because it's at 82. It's going to have to go through a phase transition, and then it's going to end at a new temperature that's above boiling point. So I've got 3 Q's that I'm dealing with. So my first Q is this range right here. So Q, maybe I could say of the liquid or something like that. This is going to be 1.00 grams times that 4.184, because that's that C value in that range. That's joules per gram degrees Celsius. And then it's final minus initial. So my final temperature in this range, the final I get to is 100 minus 82. That's my first Q amount. Now I need to figure out my second Q amount, and this is when I'm going through the phase change. So this is the phase change. And so I'm going to take my, I have to do this in terms of moles. So I've got 1.00 grams, and then I have 18.02 grams in 1 mole. So that's my moles, and then times my delta H right here, 43.9 kilojoules per mole. Notice that this one is going to come out in kilojoules, and this is going to come out in joules. But that takes me through this middle section here, and then I have to do that final section, Q as a gas. So 1.00 grams times 4.18. I'm sorry, it's not 4.184 because we aren't a liquid anymore. Now it's this term, 1.84 joules per gram degrees Celsius. And then times my final is 1112, and my initial temperature, it was still at that 100 in this range. So I'm going to make sure that I've got those 3 numbers. So I get, basically it's 1 times 4.184 times 100 minus 82. So the first Q value that I get over here, it's a 75.3, and now that's going to be a joules, remember. So if I want to make that in kilojoules, I'm going to have to divide by 1,000. So that is, 0.0753. I'll just put some extra one in, 1, 2, And now I've got this in terms of kilojoules. This one right here, the next one, 1.00 divided by 18.02 times 43.9, and that gives me 2.436 kilojoules. And then my last one, 1 times 1.84 times parentheses 112 minus 100, and that gives me, now that's joules, so I'm going to divide by 1,000. Did I get it? And that will give me 0.022, I don't know, 08 kilojoules. Now, if I want to know the total amount of Q, and most of the problems will stop right here, just asking, they just want to know the total heat. I'm going to take that number, it's already in my calculator, plus 2.436 plus 0.075312. So I get 2.533 kilojoules. So that's my total right there. If it's asking for the enthalpy change over that whole amount, all I have to do is say Qs per mole. I've got grams, 1 gram, and then there's 18.02 grams in 1 mole. So 1 divided by 18.02, and that gives me 0.5549 moles. So I'm just going to divide that by the total number of moles that we're doing this whole trick, and that will give me my delta H value. So 2.533392 divided by 0.055493895, and I get 45.7 kilojoules per mole. You might be thinking, how on earth do we figure out the sig figs? We will probably tell you what to round the sig figs to in this problem, because our software is a little funny about sig figs when you have this many different equations going on and variables. So remember, if it asks for energy, how much energy, then it's just Q. Solve for Q, you add them all up. If it's asking for the delta H, which is enthalpy, you add up all the Q's and then you divide by the total number of moles. And I know it feels like a lot of steps. If you get really methodical about it and very consistent, you'll make it through just fine.